Welcome to Complexity Made Simple. My name is Paul Allen, and before we get on to today's video, just a reminder of how you can support the channel. Please subscribe, please leave comments on all the videos because that really does help. But if you want to support the channel further, there is a donation page. Please go to Buy Me a Coffee and leave a donation, which is always fantastically helpful. Keeps the channel moving and allows me to make all of this fresh material. But if you want a textbook that contains all the good stuff from the videos, please click on the link and buy, drink tea and read the paper from lulu.com. All of these things really help the channel. Thank you to all the people that continue to buy this textbook. It really is fantastically helpful. Now let's get on to today's video. Okay, welcome to Complexity Made Simple. My name is Paul Allen, and the subject of today's little tutorial is how to properly plan a designed experiment. The phrase designed experiment is sometimes completely misunderstood. People think that what this means is that somehow you had a thought before you went to the process of which experiments you were going to do. And then you use your skill to decide which tests you actually plan into your experimental pattern. So let me show you the sort of thing that might mean. So here's an experiment where someone's got five variables that they'd like to understand, and what they've done is they've decided beforehand. So they've sat down and they've planned these 8 tests out, and they've decided beforehand. And because they've planned them beforehand, they will say this was a designed experiment. I used my skill to decide which tests it would be best to do. Now that is not a designed experiment. A designed experiment, which by the way is designed to give you knowledge, it is designed to give you process knowledge, follows a very particular pattern. There is no choice in the pattern, there is no skill in the pattern, there is only the right mathematical way to approach the test. So let me show you in a simple diagram what this would mean. Now we're going to think about 3 variables. We're just going to think of time, temperature and pressure. You'll see why I only picked 3 variables in a minute. But if we say time is going to be 5 to 10 seconds, temperature is going to be 70 to 90 degrees, and pressure is going to be 100 to 200. Here's the pattern that gets tested. We'll start with time. It's going to be tested at the low and at the high only. So we're going to test 5 and 10. Then what we're going to do is we're going to test temperature whilst those 2 tests are going on. So this gives us 4 test combinations. So this is now temperature here up the side. And obviously we're going 70 at the bottom, 90 at the top, 70 to 90. And then finally I'm going to put the 3rd variable into the test, and of course it creates this cube, which is known as a design space. And we've tested at the corners of the design space. So we've tested at those 8 places. So this one here now would be pressure going backwards, and pressure of course would have been tested at 100 at the low, 200 at the high. That is a designed experiment. It is a pattern. It is a mathematical pattern that gets the most amount of information from your tests. And I mean, I've just put time, temperature and pressure in there, but you could put any variable in here It could be things like, I don't know, if it was a molding machine, it could be hold time. Obviously, it could be temperature, could be temperature of the front tool, could be temperature of the back tool. It could be injection time, it could be injection pressure. There's all sorts of variables that could go into this, and it wouldn't matter what the process is. This pattern, if you're going to test 3 variables, this is the pattern. You're going to create a cube, a design space, and that is what a designed experiment is, and it is nothing else. If you've logically decided using your skill, that's just a 1-factor test using your skill. And by the way, you'll find out very little using that type of testing. Only these types of tests give you true process knowledge. So that's what a designed experiment is. Now, how about going through and designing the experiment? Well, in order to do this, I have a template. I don't just randomly make this up. I don't do it in 5 or 10 minutes. I will often spend, in fact, I will definitely spend 1 day filling out this questionnaire. 1 day it takes to design an experiment properly. So let's look at the questions. Pretty straightforward. What's your process? What's your problem? Obviously, what's wrong? Then it says, okay, what's your objective? Now I know what your real objective is. It's to fix that. But that's not the way we want you to think. You are doing a test. You have the opportunity to find out incredible amounts of information just out of one test if you design it correctly. So the question is, what do you want to learn? What do you want to learn? Now this might be things like, you might want to learn if there is a sweet spot with other outputs to the process. So in other words, you have a problem with one of the quality features of a machine. You can't get it to land on target. But of course, nobody would thank you for curing one quality output and then messing up 2 others. That's not an answer. You need to find a sweet spot. So there could be a sweet spot with 3 or 4 outputs that you're trying to learn. What else? You could be trying to be cheaper. So again, you might already have a relatively good process, but you want to get the same results, but maybe with some of the energy hungry variables turned down low and some of the less costly variables tuned in to substitute them. That would be a great solution. So there's more than just fix the problem. Yeah, we want to learn stuff, and you need to think that through clearly before you start. Then it says what's your start date and your end date. What this basically means is how much time do you have to do this test. Time is always going to make you compromise. It's going to make you compromise. And so you need to know, have I got the machine for the weekend? Have I got it for the day on a day shift? How much time have I got? And of course, when you've designed the experiment, you better make sure it fits in that space, because if it doesn't, you have a problem on your hands. So how much time do you have? Then it says, right, what are the responses? Obviously, there's the response with whatever's wrong in your problem, but there should be more than one here. Key thing about the responses, the outputs, more than one, so that what you can find is a sweet spot. Okay, and then it says what type of data is the response. Now the response, it must be variable data. This is because of the sample size. If you get pass-fail data, the sample size will turn into thousands. So if you don't have a variable scale, invent one. Okay, so that's very important for the efficiency of the test. Then it says, what's the anticipated range? Now, a key question really here is, can you measure the result? Can you measure the results? The reason we're asking that question, it goes back to the pattern that I showed you here. What this pattern is basically going to do is it's going to put the three variables at certain times all at their low setting. It's going to put the three variables all at their high setting. So you're going to push the process around. You're possibly going to put some settings in here that you've never used before. And therefore what you might have a jig here to measure the results in a very small window, because that's all production is trying to achieve. But during the DOE, what we're trying to do is to push the process around. I want the process to go to wild places so that I learn how that I made that happen, and then I can learn how to hit targets. So you need to just check, if I'm going to go to extreme results, do I have lots of capability on my measuring equipment to just measure all the extreme results? Next point, MSA results. Key thing about an MSA, make sure you do one. So we've got a good measurement system, so we know what all the responses are. We know that they're variable. We know we can measure it, and we know we can measure it really well because we've done an MSA. Then he says, okay, what type of factors have you got? Now on this particular sheet, I've only got 6 spaces simply because that's all that fitted on the sheet. I think somewhere on here I've got a page, look, that allows you to fill out many more, but just as an indication of the sort of information that you're going to want. What's the factor? What type is it? Is it variable? Or is it attribute? Is it C or N? Is it controlled? Or is it noise? So if it's something like outside air temperature, outside humidity, that would be noise. That's not controllable. If you want to understand what noise is doing, you're going to have to do a special, robust, designed experiment. Yeah, the way that Taguchi would have designed a robust experiment. You'll have to look that up. I'm not going to go into the detail of robust designs. They are clever little tests. They are run in a very specific way though. So if you want to learn to switch a variable off, be robust to something, then you're going to have to design the experiment to find that out. Then this is super important, the range of interest. So what's the range of interest? In other words, when we're designing the design space, look, my range of interest are these two figures, the high and the low. So for time, it was 5 and 10. Now this is where your skill comes to bear. You have to decide the size of this box. You have to decide where this box sits in space. So I chose 5 and 10, but I could have chose 7 and 12. I could have chose 10 and 35 for time. Why did I choose 5 and 10? That's the region that I considered the process would work. And it's a nice wide region. So the key point about the range of interest is they should be as wide as possible, but still make the results happen. So if you turn the temperature down too low on a molding machine, no plastic would come out. I haven't got anything to measure. That would be too far. You need the window to be a nice big size, but not in areas where the process will not work. Now let me show you why this is. We're going to wind on a variable at the low, at the high. We're going to get data. There's going to be a little bit of variability in the data, a little bit of noise in there. Okay, so that was our design space. That was our choice there. We chose those 2 points to test. Now in the case of the diagram I've just drawn, the signal, which is the rise in this thing, is nice and big when you compare it to the noise. Because the noise is a little bit of variability that you get. But imagine I'd been a little bit too conservative and I'd put the highs and lows much closer together. Now what would I see? Well, I'd get the noise here. And now, there's the signal. Suddenly I can't see it. The noise is overwhelming the signal. That's why we want the highs and the lows, the range of interest. This is crucial. The range of interest wants to be as wide as possible. We want to turn the signals up as full blast, and then once we see how the process works, then we can hit targets. Then it says, are we at 2 level? What levels have we got? 2 level or 3 level? Let's take a look at why that is. Now here, look at 2 level. I tested at the high, I tested at the low, and the relationship was a straight line. But I could have tested it at the high, tested it at the low, and the relationship might have been curved. Well, 2 points, 2 levels is not good enough. In order to pick the curve up, I would do a test known as a 3-level test. So do you think the relationship is linear, or do you think it's curved? That's the levels. Then it says which variables do we think are going to interact, and finally, how are you going to measure these variables? And this means how to set them. How are you going to set them? So, for example, let's go back up to my design space. Let's say that on the temperature on our machine, actually we don't have degrees. We just have a dial. Yeah, and we just know that if we turn it all that way, it goes to the low, and if we turn it around this way, it goes to the high. We have a pointer on there, but they've not given us a scale of any kind. So the idea of going 70 and 90 on the temperature is almost impossible. Now what we have to be able to do, because we're gonna come at this with a pattern, we have to be able to hit the values. When we say we're hitting a high, we have to hit it. When we go away to the low, we have to go to the same place. We have to go to 70. We have to go to 90. And when we come back later and we want to hit 90 again, we've got to come back to the same place. Now, in this case, what you might do is just put 2 dots on the scale and say, set it to there, set it to there. That's perfectly fine for high and low. It doesn't have to be complicated, but you have to have decided how to do this. These are not random tests. The pattern, that design space, must be completed as designed. So how are you going to set them? So some variables will already have a scale. You might have dials, you might have LED controls that you can easily set. Some of them might be you're sharing cooling water. And somebody says, when we've got 3 machines on, the cooling water gets pinched and the machine doesn't work as well. When I've only got 1 machine on, the cooling water works great. How are you going to set that? You have to figure it out. You can't just turn up on the day and just make this stuff up as you go along. We have to design the standard operating procedure, design the experiment. Now that we know all the variables, now we're going to set them. Now we can go, okay, what's the sample size? Now the software, the technique itself, design of experiments, is looking for 30 to 50 samples. Okay, so you need to assume they will all be defects. You're going to push the process around to the edge of that design space. There's a good chance. That's not where the good product sits, in those corners. Everything will be defective. So you have to take that on the chin. So sometimes this makes people panic with doing a designed experiment, but typically you're doing the experiment because something's costing you money. 30 defects at this point is normally cheap. Then you say, which design types do you want to use? So there's a design technique which is known as screening. There's one which is known as modeling. There's one I already mentioned, which is robust design. You could also have 2 level. You can also go to 3 level. Okay, so you need to decide what it is you need to know and how you think your process works, and then you can decide which experiment out of that list you're going to pick. Then it says select the best approach. Now this is going to be a compromise. Cost is going to be on one side. Knowledge is going to be on the other. You can make the test cheaper if you wish. But if you do that, you have to give up knowledge. The cutting down sample size, cutting down tests, etc. It saves you time, it saves you money, yes it does. But it also, you have to give up knowledge. So you have to be prepared to give something up if you're gonna cut the corners. If you really want to know how the machine works, do the test as planned, as published, as recommended. Take 30 to 50 samples, learn loads about your processes, and make shed loads of money. To me, the best way to save money is to be at this end of this scale. Be at the knowledge end. Learn how your process works. Then it says, can all the runs be randomized? Randomization is a technique to protect you against variables that you didn't consider changing during the test. So if I go back to my design space a second, these 8 tests look like this. I'll just put them in as the minus values represent a low, the positive values represent a high. So we'll just put the pattern. And this is the pattern that describes this cube. Okay, so there it is. A, B, C. Now you could just do them as those 8 tests there in the order that they're published. But if you do that, you do run a risk. And you run a risk of I'll call it RV, which is a random variable, a variable you haven't thought about. Let's say it's the temperature of the machine, and the temperature of the machine starts to increase as you work down this pattern. If the temperature of the machine has an effect, its effect will actually show up as belonging to the first variable, whichever the first variable is, and we chose to put time in there. So time gets a sort of bonus effect if you don't randomize. Okay, so if you don't randomize. If you randomize, on the other hand, you protect yourself from that effect. Now, the question is, of course, randomization, it costs money. Okay, so typically your setups are longer. So you have to decide whether it's worth the longer setups, whether you think you might have a problem with a random variable causing your results to be false. Personally, my view is I don't randomize. And I don't randomize because what I try to do is to remove all variability before I even attempt a designed experiment. If you do that, I typically find you don't have to randomize, and that tends to be my procedure for getting around this. But there's times in the past I've done it when I haven't been confident that I can remove all the variability, and I've randomized the test. You have to think. You have to think about this. Do you think there might be random variables that could blow your test off course? If so, randomize. Then it says conduct the experiment, record the results. Best advice I can give you, be there. The test has to happen as published. It has to happen in this pattern here. It has to happen like that. If for some reason you get to a particular setting and you can't hit the pattern, then you're going to have to decide on the fly what to do. If new material arrives on the machine halfway through the test, you need to make a note of that. maybe the machine breaks down halfway through the test and a maintenance technician gets called, he has to replace something. You need to make a note of that. You need to just make a note of everything that's going on during the test, because they can all blow your results off course. And the only way to do this is to be present. Don't give the test pattern to a technician and ask him to run those 8 tests. He won't know what he's doing. He won't know why the tests are the tests they are. And if things change, you won't think anything of it. So be there and record everything that happens. Then do the analysis. And a key point, do a confirmation test. Do a confirmation test. In other words, what's a confirmation test? You make a prediction. This is when you really know how your process works. You make a prediction and you hit it. That is confirmation right there. And that proves that you've got knowledge out of this experiment. That's what a DOE does. It gives you knowledge to be able to predict and therefore just hit targets. You've proved nothing until you've done that confirmation test. And this should be true, by the way. However you think you've solved a problem. If you think your skill has solved the problem, well, do a confirmation test. Make a prediction of what's going to happen. If you hit the prediction, then you've done a pretty good job. If you don't, start again. But the confirmation test is the true test of whether the DOE has been successful or not. If you confirm, well done. And then finally, document your decision. Put it in your ISO documents maybe. Make sure you keep company records of what you've done. Too many times, too much testing is done informally. And when that engineer or that scientist walks up the road, he takes that skill and knowledge with him. If you do a proper designed experiment and you document it properly and you keep the records, that process, you will always know how that process works, and the engineer can walk and find a new job anytime he likes, and you don't care because you've got company knowledge about how your processes work. Now there's the template. That's what I do. I always fill that out. Every time I do a designed experiment, it takes me a day. Most of the day is spent on this page. Most of the day, to be quite honest, is spent on the table at the bottom here. What are the factors? You're going to get a team of people, all your technicians and operators. They're going to sit around talking about their pet theories, about what makes this particular problem come and go. There's going to be lots of discussion. You will have to decide the range of interest. That will challenge them enormously. They've never been asked that question before. How to set and to come back to the highs and the lows. They've never been asked to do that before. So there's a whole lot of challenging discussion to be had. And often half of the day is spent on that table. But spend one day designing an experiment properly. Design a proper design space like that. Get fantastic process knowledge, and then smash your competition out of the water and make piles and piles of money.